Okay, so I'll start. Good morning. Uh, first hour, I'll be talking about this one, the Kuhn semigroup of stable rank 1 sister algebras. Recall that for stable rank 1 sister algebras, we have already seen that Kuhn's comparison is rather especially well behaved. We've seen, for example, that sorry. So suppose A is a sister algebra. It's stable rank 1, then A is equivalent to B if and only if epsilon there exists unitary in the algebra or in the unitization such that U A minus epsilon plus star is in the hereditary algebra of B. Also, that's Chipuerca. That's even only if it's about x star and x is in the hereditary algebra generated by B. This only regarding Kuhn's comparison. If you go to the Kuhn semigroup, that's already in the first paper by Elliott. And Ivanescu. We didn't talk about it, but CO of A is especially way behaved because it can be described in terms of isomorphism. Classes completely generated here with A modules. Okay, the Kuhn semigroup, as introduced by Coward, Elliott, and Ivanescu, was in terms of Hilbert A modules and a relation over them, which was not isomorphism or sub-isomorphism. For the special case of stable rank 1 sister algebras, you can see that the thing that they describe is exactly isomorphism classes, of course. Then another thing, like this is round tons. So they prove that A is actually hereditary of A. This meaning that Y is here, it's not Y, then X is also present here. This is an important thing in order to study the behavior of the non-stabilized Kuhn semigroup inside the stabilized one. And also, I think you already had a. No? No? Okay. Isn't the Z stable case in here in the book? Maybe it's just an observation. Okay. and that's 11, probably. Or a special case. I don't know. We don't know. Okay, then also another thing. Jordan Winter, that will be weak cancellation. Weak cancellation is that if you have x, y, z, u of a, such that x plus z way below y plus z, then x is less or equal. Well, okay. This is a way of cancellation, but you need a way below in here. This is equivalent to proving that x plus z less or equal 1 plus z prime with z prime, something that is way below z, then x is equal to 1. So there are different forms of weak cancellation. This is a way to spell it, or this is another one. And I'll probably prove this one, but recall this definition in order to say that the elements we are dealing with, we can assume they are way below some things. Because I want to sketch the proof. Not so of the weak cancellation. Weak cancellation. If I need it, I'll spell it like this. So by looking at this, that we can assume things that are way below other x and z are already way below things. We can assume that x equals class of B and C with x oh. I think I don't actually need this one. If sorry. If you're already dealing with some matrices in the algebra stable rank 1, its matrix will also have stable rank 1 and also a unit cell, because if you go to the unitization, you will still have stable. So let us assume these things. First, suppose C is a projection. And in this case, also but B is also not to A, so we have a sub equivalent to also B. So we have this situation. We still going to further matrices here and considering 2 by 2 matrices, whatever, we can assume these things are orthogonal. Note that A minus epsilon plus is actually only multiplying by epsilon because this is because P is a projection. So this implies that there exists a unitary U such that U a sorry. Is in the hereditary algebra of B plus B. Okay, and this hereditary algebra, since it's a hereditary subalgebra of A, which has stable rank 1, this also B that also has stable rank 1. Okay. So in B, there exists, so you have B, which lives in B, there exists B, which is also, you can go for it, the unitization of B, which will already lie inside the unitization of A. Such that B star sorry. And this U star is in the hereditary algebra of A, and then in here, sorry, that U star lives in this hereditary algebra, and it's equivalent to B. So in B, there exists a unitary such that B star B holds. This is an hereditary algebra B. I can go from this one to this one with a unitary. They are projections, so there will be a unitary equivalent. And B star U B B is B star U B plus B U star B B. This would be P. This would be an orthogonal sum. So this star, so this is orthogonal. So okay, so this star U minus epsilon plus U star P is in minus E. Okay, so this is orthogonal to this part, so this is it, and it's in the hereditary algebra, so it actually lives in here, which is already so this has this B here, so this is in B. Well, this is not closed, but this you have to close it. So this is telling you that A minus epsilon plus is sub-equivalent. So this is in this hereditary algebra, this is sub-equivalent for epsilon. I've never taken epsilon. Okay, so this in the case of P being a projection, and in general, well, in general, we are ready in this case. So, who is it? Z. This is, and this is a projection now uh, by O5, which Loran proved the other day, and applied to this is that right? Then it sees W such that 9 plus W is less or equal to 1, which is less or equal to plus W. Hence, here, right? It's plus Z is less or equal X plus 1. X plus 1. Is less or equal X plus Z plus W, but X plus Z plus W here is less or equal Y plus Z prime plus W, and Z prime plus W, this is less or equal Y plus 1A, but since you can cancel projections, this implies that S is less or equal. Okay? Okay. So we have this other axiom of Wick cancellation. Still more axioms that you have in case of stable rank 1. Let me write it correctly. Ah. Let me write it this way. So there is an axiom O6 and O6, sorry, and an enhanced version of this axiom proved by Hannes. O6 is actually almost Ries's axiom. Says the following: if you have X, it's Z, then there exists E X is E, which is less than like F, which is less or equal to Z, such that it's less or equal to E F. Okay, so if you have this condition, then X is covered by Y plus Z. You can somehow translate this sum into something that lives inside X. You can find E and F, which are below X, and each of one corresponding to this part in Y and this part in Z, such that X prime, something way below, is covered by E and F. Actually, this statement, you can state it only talking about E and then changing this F to Z. So you will obtain the complete statement by doing the same recursively 2 times, and it's good for as many sums as you want. And this is what I'll do with 6 plus, because the same is that in X prime, this is the same. There will exist E, which is way below X and Y, such that X will be below plus Z or some E, which is plus and Z. But the thing is that this element, you can put it above any other B which you had at the beginning. So if you first started with something that is already below Y and X, you can you will be able to do this O6 axiom, slightly improving the element that you've used before. So this is the enhanced version. Now let me say this is true for all sister algebras. This is only for Funnels already provides an example of some algebra which does not satisfy this action. It does not characterize stable rank 1, but okay, so more things that you can do. This interpolation, probably way I'm saying this. This one. Here, if you want to have Z1, Z2, that's equal to so then there is this Z such that Z. Let's see. Z or then here the proof, which will use many of the things above. First, it is enough to find This is basically by CU properties. You have Z1 prime will below Z1, Z2 will below Z2. Each one of these is less or equal. It's two. It is enough to find some y which is still below. Okay, this is basically CU properties. You can do it with cutdowns of these elements and it's put something which is way above these ones and below this. Cutting down these ones would only complicate the things. So case X1 is compact. Plus this case. So Z1 prime is way below Z1, which is less than equal to X2. Z2 prime is way below Z2, which is less than equal to X1 and X2. In here, you apply O5. So you can you apply O5 to this part. So there exists some W such that Z1 prime plus W is less or equal this one, which is let me write this one here. This is less or equal Z1 W is less or equal. Now Z1 is less or equal X2. X2 plus W. Okay, and for this one, you will use O6 plus to find X1 is less or equal to B plus W, and so let me write again. Oh. Wait. So I'm applying O6 here. X1 is way below X1, which is covered by Z1 and no by X and this. So here is where we are applying O6 plus. So X1 is less or equal to T plus W with some T, which is less or equal to X1 and X2. So I'm applying O6 plus to this thing, which is less or equal this thing. So this is the O6 plus I'm using, and I am also improving this Z2 prime, which I had before. Oh. Okay, and what else? Here, Z1 prime plus W is less or equal here. This is the same as I had here before, but now I can apply weak cancellation to find that Z1 prime is less or equal to T by applying Z weak cancellation here, and already Z2 prime is less or equal to T. Okay, so we have an element T, which is way below X1 and X2. These are wanted, which is above T1, above Z1 prime and Z2 prime. Okay. O6 plus is also good. Or O6 plus. Um, and now, so we've done this for compact elements. We wish we could do this with some abstract nonsense in terms of CU semigroups to go to the general case, but this is not possible. For the general case, we use the following. Which is if a stable and if an element, positive element, there exists a sister algebra and a projection B such that the following happens. A is as a close two-sided idea in B. It's in CU of A. What's this? Well, if and only if and only if it's less or equal to A is U of B, and if A is still around 1, then so A. Okay, so this is a result about C-star algebras, which will allow us to this thing that we've done with compact elements, do it for general algebras, going to a larger algebra in which we have a projection, which will play the role as a 1-to-1, and comparing elements with this A is the same as comparing them with the projection in the big one. It's naturally technical and it's C-star dependent. I mean, it's something you can, or we haven't been able to construct in terms of CU semigroups. Well, if someone does that. Okay, I won't do the details, but this is as far as the sketch goes. And well, using this interpolation, if A separable, then given X and Y and CU of A, it's abelian is such that it's way below X, Y is vectored. I mean, this is, you don't need separable for this, but if the algebra is separable, this is countably based. which means that this being upwards directed will have a supremum. And the supremum of the elements which are way below x and y will be the infimum of these two elements, namely. Okay, so you can build infima of elements in C of A if you have a separable C star algebra. Obviously, here I'm only thinking A has stable rank 1. That's general thing. And moreover, operations are somehow compatible with the addition. What we call if ordered CU semigroup. Okay, so there's a if A has stable rank 1 and it's separable, then the Cuntz semigroup has a lot of structure, which is actually a new semilattice ordered CU semigroup with cancellation and so on. So there's a lot of things one can do in here. So let me write some applications. In what I say applications, it's what applications you can do of all these structure that stable rank 1 and C-star algebras have. Recall that if A, well, start with a conjecture of Blackadar-Handelman conjecture. If these units are, recall that we already discussed his isomorphism for dimension functions of A, where exactly the states on the Cuntz semigroup is only 1, which is actually the same as the states A0 star of A. And in here, what we used to prove the existence of stably defined C-star algebras was the existence of lower semi-continuous dimension functions of A, which were the ones that were isomorphic to the quasi-traces, okay? And this was what Blackadar and Handelman proved. They showed that this is a Choquet simplex, and they conjecture a couple of things, but one of the things that they conjecture is simplex trajectory. So this structure is way larger, but since you get simplex, they seem to have a nice topological structure or analytical structure, then we expected that this will also have it. Well, if Google proved that D is a get simplex, if and only if 0 of A is interpolation, is well, this is what Kudra proved. This is data. This happens if and only if W of A has interpolation, and using no longer in the blackboard, but the fact that this is hereditary, if CU of A has if CU of A has interpolation and the algebra is hereditary, then this will also have interpolation and you'll have a showcase simplex. So for a stable one. Okay, so something you can prove using Kuntz semigroup techniques. How this enhances structure. Only actually, here also hereditariness and the fact that this has a interpolation, as we proved. Another thing. Globally halving, this has multiple statements, but the question I will be addressing, it's probably not always interpreted in these terms, is if A is sister algebra with no dimension of agent. Does there exist? That's a question that goes from the continuous functions to a oops, sorry. To So well, let's say that we wanted to address this question. Where can you find algebras that admit this kind of maps? There's a whole lot of interpretations in terms of some theorems of Klim that why this is related with this finite dimensional representation. Once you have this Klim already proved that any representation of the system, this is equivalent to the algebra having representations of rank greater than n. So once you have one of these non-zero maps. So are you able to create these maps with full range? Actually, the halving will be with the two here. Well, just to give some idea of what's happening, maps from continuous functions from 0, 1 to m in to a can be described in terms of CU. But not actually contra comparison, and that's Rosen and Winkler. I think there's a cyclic thing of references in the literature for where does this thing goes. But if you want a map that takes the element that I mentioned to go to the I. So to build a map from here to here, you can build such maps if and only if you will need I to be mutually orthogonal. And this, I mean, example, they are all equivalent to 1 and orthogonal. So this is the way to build a map in one of these maps. So in the case of, this is not actually Kuntz comparison, it's a little bit stronger. But in the case of stable rank 1, this is already exactly what you do. You can do your arguments in terms of Kuntz classes and then build your map in here. So for given A, no? So if you have an element A which is full or has the ideally generates, as algebra generates is full, you will run to see if you can build n copies of A. If you can build n copies of some element C are less or equal A. So can you build a map that goes here? So if, for example, you take 1 and you build something which is supposed to be full. So if you can somehow divide your elements with also full elements, you can then use these Kuntz classes to build maps that will satisfy what you want. Well, this is just an idea I mentioned. This was studied by Robert and Rodham, and they show that if A has no irreducible representations dimension less than K, then one, assuming a unital, which is actually compact, is what they call Kn divisible. This Kn divisible will mean that there exists one y n such that Ki is less or equal 1 for I, and the element 1 is covered by 1 plus yn. Okay. Well, the thing that all this element is covered by some different pieces, which are actually somehow divisible. This allows you to build a map that goes from okay, which is cool. Okay, so each of these yi's will allow you to build a map from one of these components. This C is the column, it's the continuous functions to mk. And each of these will allow you to build one map from here to here. And it will be full because the images will somehow cover the unit. Then using Infima, one can build taking Z. So that's in general, eh? But now if A taking Z to be the infima of these yi's, well, one k y is less or equal 1, and y is also full. Kz, sorry. And you have to go way above this one, but I mean that whatever. The thing is that it will be full, well, for some finite else. So this allows you to build a map that goes from mk a, which is full. Okay, so the thing is that for stable rank 1, this is what Robert will say. For stable rank 1, you can prove that if A has no reducible representations of dimension less than k, you can already build these full maps from the cone of matrices to A, which will give like the block of the target. And I'll be very quick about these things. Very quick because I don't have time. But another application which I already also wanted to mention is the realization runs Okay, so this is probably, I guess, Loran already talked about it. If you stay with the Kuhn semigroup and you consider the generalized trace, not only normalized, and this taking probably infinite values. These are the same as the functionals in CU of A. Now, for each element A in CU of A, one has these maps that goes from the functionals CU of A to 0 infinity, which is what we call a rank, like the different rank you can associate to an element. So there exists like the properties you're getting here are not all possible lower semicontinuous, or not clearly if they are all possible lower semicontinuous functions of this type, but you have this map that goes from CU of A to a certain notion of dual. Yeah, so it's already defined. Okay, sorry for that. LFCU A of semi-continuous functions on the function CU of A. Okay, so one studies which is the range of this map. Well, then using A as stable polynomial, one can define alpha that goes from here it's only a map given you start with the function and you take correctly. Schema of X and CU A such that is way below F for all. Okay, so you build this, but this need not necessarily be upwards directed, and it is upwards directed in case A has stable rank 1, so it's well defined. But the map is whatever. I mean, there's so many associations. Usually not even additive. Note, for example, if A is the complex numbers, probably this in this case has a nice description, and this can be described in terms of like a tensor product. Tensor product in CU, which exists. So there's some work to be done here. So this is 0 infinity, and it's clear then this map that will go from so this is like 0 infinity, goes to the natural numbers, and I think it's clear that this takes an element x. The floor function, well, that it doesn't have much structure. It's not even additive, and actually, this I think this boils down to be the only obstruction for this map to be well defined and be an additive. But it also the obstruction to being subjective. So one can prove that if value is not so. Also to build this, you need separability. Well, I'll finish now. Stable rank 1, and as you know, elementary quotients. Okay, so this would be like your obstruction to many things, additivity in particular. Then for all F, B, and A, there is 7. Let's start. Okay, so all the functions in here can be realized as rank functions, and in order to get these elements, you can use the map alpha. That is this composition is the identity, but not all elements zero of A can be are actually coming from one of these alpha. Okay, and sorry for taking some more. In order to prove this, you naturally have to use the infima, but many other of the properties are stated before. Okay, so we'll take 10 minutes and we'll continue.
Okay, so welcome back for the second part of this last session. So in this last hour, I will present more abstract properties about Kuntz semigroup, and namely, we will study more in depth categorical property that are satisfied by CU. So the first thing is to show that the category CU is B-complete. So it admits small limits and colimits. And so I will briefly recall some categorical facts. So whenever I have a full subcategory C inside D, there is this nice characterization of being a reflective subcategory. So it means that the inclusion functor has a left adjoint that we will conveniently call gamma. And also it's also equivalent to kind of a universal construction. Okay, in the same way we've seen how to complete a pre-Kuntz semigroup into a Kuntz semigroup. Okay, so it means that for any map from D to another object C prime, which belongs to C, there is kind of an extension of this map from the completion of D through this reflector, and alpha extend uniquely from the completion to C prime, now in the small category. Okay, so an observation here, C will be CU and B will be pre-CU. Okay. So this gamma is called the reflector, and actually this gamma gives you this object and this morphism, which are the completion of any object D. Okay, and we have some nice property, and so is that reflectors, they pass any colimit from D to C, and a fortiori, if D is co-complete, then so will be C. Okay, so this is the main plan of attack that we will use to show that CU is co-complete. Okay, and I recall also that a category D is co-complete, which means as admits any small colimit. This is equivalent to having co-equalizer and finite coproduct and direct limit. I mean, yeah, direct limits of inductive system. Okay. So this nomenclature is always a bit confusing, but this is a colimit. Okay. So the nice thing for the co-completion is I already construct. We've already seen that CU is a full reflective subcategory of this category pre-CU that we use for showing the continuity of the functor CU. So we already know that CU sits inside pre-CU in a reflective way, is reflective subcategory, and we know what is the reflector, which is this gamma, where we constructed the increasing sequence for the auxiliary relation on the pre-CU semigroup, and we quotient out by some equivalence relation. Okay, and so we use this reflector to actually pass direct limits in pre-CU to direct limit in CU, and we show this way the continuity of the functor CU. So we already have this thing, and so from this theorem or property of reflectors, I only need to show that pre-CU is a co-complete category, right? So I only need to show now that pre-CU has finite coproduct and co-equalizer. So the theorem can be stated as follows. Oh, probably I should mention that all the results that I will be stating in the following hour are from Juan Pereira and Dil, and probably they have been published between 2018 and 2020 or 2021. Probably. Okay. So I will not mention, but all this work is from this group of people. So theorem, the category CU is co-complete. Okay, so proof, sketch. So we already know that CU has direct limits, and it is enough to show that pre-CU has finite coproduct and co-equalizer. Okay, so the finite coproduct is really, I mean, I don't want to say trivial, but it can be easily checked. And let me just make a sketch of Okay, so this, I mean, it just construct an algebraic object from these objects in a usual way with inclusion maps, and those will be pretty morphic. It's not so hard. And co-equalizer is well, the hard work is happening, and I will only briefly mention how to construct this co-equalizer, but I will not make the proof. So I recall that they correspond to a small diagram of two objects and two arrows coming from one object to the other. So I have my object S, and I have two arrows, right, from S to T, and okay, so I have this small diagram in pre-CU, and I want to find the colimits. I want to find an object and arrows that goes from, it's enough to find an arrow from T to the colimit such that it satisfies this universal property of the colimit. So to do so, this is based on the following construction. So we will first define a binary relation, which will not be transitive, but that we just take the transitive closure afterwards. So how to identify two elements of T. So whenever I have two of those, I say, I identify T1 and T2 through this relation. Whenever I can find the element in T and two elements in S in the domain such that the following happens. So T1 can be written as this element set plus the image of the first element through alpha and the image of the second element through beta. And I can write T2 by inverting the images. Okay, so T2 will be the sum of this element in T and plus the reversed images. Okay. So it's not hard to see that this is almost an equivalence relation, but it needs the transitive part of it. So we will conveniently define the transitive closure. And now we get an equivalence relation, and we can just project T onto these quotients. Okay, and this will be the morphism and the object we were looking for. Okay. So this map and this object, it's easily seen that it's a co-cone for this diagram in pre-CU. And there are obviously some work, definitely not trivial work to do to show that this belongs to pre-CU. One should specify what's the relation there and so on, but more or less that's how we construct co-equalizer in this category. And then using all this categorical general knowledge I recalled, we show that pre-CU is co-complete and henceforth CU is co-complete. Okay, and actually to get the explicit limit of any small diagrams, you first compute it in pre-CU, and then the co-limit in pre-CU, you just plug it into alpha, into gamma, the reflector, and it will give you the explicit co-limit in CU. Okay. Okay, so second part is co-completeness. So this is the nice thing about category theory is that now I just have dual notions of all of this. So now I have a full subcategory with this inclusion puncture J from C to, I changed the name not to get confused. And it's co-reflective, it's if and only if it has a right adjoint that I will call tau. Oh yeah. And it's equivalent that any object in E admits a co-completion. I will call tau of E and tau E in I think I made it. Here was C before. I made it. Anyway. So it's a pair of an object and a morphism that satisfy this universal property. So now we just have to reverse the arrow. So for any arrow from an object in C to an object in E, I can go from, okay, I reverse the arrows. So now I go from this co-completion tau of E, and I can factorize here. Okay, so this morphism also is in C. Okay, so it's just this dual notion, and the proofs are the same. And now conveniently, E will be the category Q that I have not defined yet. And now we'll have the same properties. So co-reflectors pass any limit from E to C, and recall that the category I is complete if and only if it has equalizer, finite product, and inverse limits. Okay. But now we don't have all these things, so we have to do something similar. Okay. So to do so, we will define a new category, okay, which is larger. And so this is also Antoine Pereira and Till in 2018. So it is this larger category. So the object will be this guy. So I have a pair where S is a positively ordered monoid, so it has a sum and an order, and they are compatible. And it also has, okay, I think it has been defined before, but it has an auxiliary relation, right? You can think of this to be transitive and usually non-reflexive. Okay. And we have the following properties. So this auxiliary relation is additive and positive. And S satisfies O1 and O4. So recall that O1 means that it's closed under suprema of increasing sequence, and O4 is that those suprema are compatible with the sum. Okay. And if we have such a pair satisfying all these things, we say that this is a Q semigroup, that S together with this auxiliary relation is a Q semigroup, and Q morphisms will be so a monoid morphism from two Q semigroup that preserve suprema and the auxiliary relation will be a Q semigroup. Is Q morphism. Okay, we have this category, and it's built in such a way that Cu will sit inside as a co-reflective subcategory. Okay, so first observation, which is easy to see, is that Cu is actually a full subcategory, and to a Cu semigroup, I just explicitly specify the compact containment relation. Okay, this will be an auxiliary relation that satisfies this additivity and positivity property, and obviously S already satisfies O1 and O4, and even O2 and O3. And yeah, any Cu morphism between two Cu semigroup will preserve slope and compact containment, so it fits. Okay. Okay, so now what we have to do is to construct this right adjoint, which is the co-reflector, and which means we have somehow to find this co-completion thing. So how to do so? So we will consider this set IQ, which is all the rational number that are contained in the open interval, and we define kind of this auxiliary relation given by this thing, okay, the strictly contained. Okay, so we don't have any addition there, okay, but we can look at this map. So this is just a set with auxiliary relation, and it's positive, but it's not so important. And we define the set of map F from probably. So for Q semigroup, I can define P of S to be the map from IQ to S. That preserves the auxiliary relation. Okay, I don't ask anything about, I mean, I don't have additive structure there, so I don't ask anything about these things. I don't have suprema in some sense. So I only ask that this those maps preserve the most auxiliary relation that I have. Okay. So what it means that whenever I have Q prime strictly smaller than Q, I want that those images compare with this auxiliary relation. Okay, there's nothing crazy here. and those will call path, and we consider a superequivalence relation on the set of path. Okay. So how to define the superequivalence? So we say that a path F is superequivalent to a path G whenever the following is happening. So for any rationale here, I can find a rationale that is closer to 1, such that the image of the smallest one by F is covered by the image of the biggest one by G. Okay. So, yeah. I mean, this superequivalence will be compatible with, I mean, we can have pointwise addition and order in the set of paths, and this thing will play well with this structure that we have. So, observation, yes. Is pointwise addition, okay. So it means that F plus G will just be to a rationale, you just send the sum of the two images. And by desymmetrizing the superequivalence, we get an equivalence on the set of paths from IQ to S, which naturally gives us another monoid. Okay. And this naturally comes from the superequivalence. Okay, so a class of paths will be smaller than a class of paths if any of the representant is superequivalent to any of the bigger class. Okay, so I'm not putting details, but this is a kind of a usual construction. Is not only an order monoid, but a positive order monoid, because it's not hard to show that any path will be, I mean, the zero path belongs to PS and it's superequivalent. I mean, there are a lot of small things to check, but it's true. And okay, it's probably, and moreover, we have a natural map and it's going to be a monoid map. Another monoid map from this guy to back to S. Okay, that I will call conveniently tau S from so to a class of path. I just look at the supremum of all the images. Okay, so why is this well defined? So there are two things to check. Is first that this thing is increasing. I mean, we have, yeah, it's countable, so it's, I mean, you can always consider it's a sequence. And I didn't say, but auxiliary means also that we have this property, okay? So the set of pairs that compare with this auxiliary relation are inside the set of pairs that compare with the other. So it means that if, and because this is a path, I have f lambda prime compare for this relation to f lambda whenever lambda prime is strictly smaller than lambda, and it means that they will also compare with the other. So we have something increasing here. Okay, it's indexed over the rational, but you can use a bijection. It's countable to actually consider this as a sequence. And since S satisfies O1, we can take the suprema. It would also be something in S. Okay, so it's well defined, and then you would have to check many things that it's compatible with the sum, with the order, and we will even have more than that. Okay. So I know. And okay, this theorem still Antoine Pereira and Tim, we have the following. Well, first of all, this thing is in fact a CU semigroup. Okay, so this takes quite some work, but it's been constructed in such a way that we would get this theorem. This map tau S, in fact, is a Q semigroup. So it means that it also preserves suprema of increasing sequences, and that blah blah blah. Whenever I have something that is way a class of paths is way below another one, then these things compare with the auxiliary relation. Okay, and in fact, this pair of object and morphism, okay, is the pair I was looking for. That is the universal co-completion. Okay. Okay, so it means that for every okay, so for every map from every map from a CU semigroup T to S. Okay. I can factorize it through this co-completion of S. Okay, so now this will be tau of S, and this is tau S. So it's called the endpoint map because actually this can be seen somehow as the value of F at 1. Okay, it's the limit value. And there exists a unique CU morphism that this thing commutes. Okay, so this says that In other words, yeah, there are many reformulation that tau from Q to Cu is a coreflector, or Cu is a coreflective. Full subcategory of Q. Okay. And as a corollary, we will be able to show that using this thing above, that Cu is complete. Okay. I don't have time to get into the core of the proofs, but the main point is I show you how these things are constructed, and then you kind of have to believe me that it works. So proof or sketch, at least, from this general knowledge of category theory, it is sufficient to prove that Q is complete. And it's the same thing, is that Q is easier to deal with than Cu, in the same way that pre-Cu was easier to deal with than Cu. Okay. And in this case, we will just show that it admits any kind of small limit. Okay. So start with a small diagram F in Q. Okay. So we have a functor from a small category I, and its image will give us a small diagram in Q. And the way to construct the small limit is to do the following. So I will use the fact that this category of positively ordered monoid has actually products, but it's not so hard to prove. It's an algebraic construction, so it's done in the usual way. And now I just consider this object. So this will be sets of element ordered by the number of objects I have in my small category, and they belong to, okay, the product of, okay, so in order, I mean, I can just forget the extra structure and look at this object in this small diagram as ordered monoids. Okay, I realize their product in as ordered monoid in this category. Okay, so it's an algebraic object. And so I consider all the tuples that lives inside all of these objects, and that satisfies the following property. So every time I have an arrow from one object to the other, I want that this arrow is sending the element of the tuple onto the next one. Okay, so for all arrows that I have in my algebra. So associated with this, I can trivially define projection map. I have a map Pi from S to Fi, and it's just projecting onto the component that is needed. Okay, and so here I have component-wise sum and order. And so it makes this thing an order monoid, and those maps are order monoid maps, and you can show that if you apply the forgetful functor to this functor, so you get a small diagram in POM, this actually is the way to construct the POM limit. Okay, so the limit in POM, and so we have the POM limit of F recomposed with the forgetful functor, so let's call it mu. So this thing goes from I to POM. Okay. And now so there is a lot that I'm not proving, obviously, but in order monoid category, usually it's pretty much algebraic stuff that goes on, and it works fine. And once we have computed this, it just we only need now to observe that if those guys are in fact Q semigroups that are equipped with this extra auxiliary relation and they satisfy O1 and O4, then this S will be equipped also with this extra relation, will satisfy O1 and O4, and those PI will preserve suprema and the extra auxiliary relation. Okay, so moreover, if Fi satisfies O1 and O4, and Fij reserves sup, okay, then so is S and Pi for all I, okay, so this is and finally, we define an auxiliary relation on S just component-wise, okay? So we have that S is covered by T. This, by definition, means that Si is covered by Ti for all I. Okay, so those are tuples, I recall. Okay, and then you can show that okay, this relation is what we want, and this makes S a Q semigroup, and pi a Q-morphism, and this will have the limit property, the universal property of the limits. So is code in Q for diagram for F for I, and in fact it has the universal property, so it is the limit. Once again, I just stated what's true, but it needs to be proved. Okay, obviously. Wow, I'm already out of time. So in the last 5 minutes, I just want to mention tensor products and the fact that the category CU is a not only monoidal category, but it's also closed. So the monoidal structure on CU. So yeah, to go really quick, there exists a B-functor that goes from Cartesian product of CU categories into CU with a unit, which will be the completion of the natural number, that makes CU a monoidal category, and not only monoidal, and in fact it's also symmetric. Okay, so the proof is based on the monoidal structure available in the category of positively ordered monoids. Okay, so also this is a pretty standard construction that is based on the free monoid of dual monoid, and you take a quotient and then you just identify things that you want to identify. But let me just mention that this is very technical, okay? And yeah. Okay, and C, really quickly, closeness of CU. So the closeness means that this tensor product thing has an adjoint, okay, which is called the internal Ohm functor, and it will be based on this tau construction of path that I mentioned earlier. Okay, so okay, probably it's here in the tensor product. I mean, so we have to define this CU B-morphism. So all these things are object in CU. It is a CU B-morphism if it is generalized CU morphism in both variables. So it means it preserves some order and suprema on both variables, and we have that the image of a tuple is way below and compactly contained the image of another one whenever, and this is not component wise, we need that both are cut downs. Okay, so this is something stronger. And we have this nice thing that also happens for other monoidal category is that the set of BC morphism from the Cartesian product of two objects with codomain a third object. This is in bijection with the CU morphism from the tensor product of the two objects of the domain. Okay. And now how to build the internal Ohm functor is that the set of generalized CU morphism from two CU semigroups, so it's those maps that preserve everything but the compact containment relation. We can equip them with this auxiliary relation given by I mean, the usual thing. So the image compare for the compact containment relation whenever this thing compares. Okay. So actually, a morphism, a generalized CU morphism will compare with itself for this thing exactly when it's a CU morphism. Okay. And once we have this, so this, oh, I forgot to say, this is a Q semigroup. And so we can apply this tau construction, right? So this co-reflector, and we have this thing that the set of CU morphism from the tensor product of S and T into P is in bijection with the set of CU morphism from S and now this tau construction from T to P. Okay, so tau of okay, so this exactly says that the functor this functor is the right adjoint of the tensor product. I mean, for all three, I have a functor that makes a tensor product of the object with T, and this is the right adjoint of this functor of T. Okay, so I think the notation is like that. Okay, so it's a closed monoidal category. Okay, sorry for the overtime. And yeah, this was more like presentation than proofs, but yeah. So thank you for sticking with the course. I hope you liked it. And, probably see you next time. Yeah.